Hello students, in this lecture we are going to start with system of particles and linear momentum. We will be discussing conservation of linear momentum in detail, and also we will take a lot of questions based on it. The link to the PDF is in the description. You can download it from there. So first of all, let us understand what is momentum by taking a very basic example. Here, visualize there is a truck that is approaching towards you. In this situation, truck is very heavy compared to your body. So, will you die if the truck collides with your body? Another question. Imagine a very light particle is thrown towards you. It is coming towards you. In this situation, are you going to get injured because of this? So, in both these cases, how we will judge what force will act on our body because of the case given to you. So here the crucial part, the most important part based on which we will be commenting on the force is mass and velocity. To understand this in detail, we have to understand momentum, which is product of mass times velocity. So if you know that whenever an object is in motion, then it will definitely have some linear momentum. So firstly, it's a vector quantity, means it depends on magnitude as well as direction. To understand this, let's take an example. Here we have a mass m that is moving in the right direction with velocity v. Another similar mass moving in the left direction. We need to comment on whether the initial momentum and final momentum is same or not. So as you can see, momentum is a vector quantity. It definitely depends on direction. As the direction changes, momentum also changes. So mostly students do this mistake. They tend to think that momentum is product of mass and velocity. So if magnitude wise both are same, momentum is same. But momentum is a vector quantity. So definitely it will depend on the direction. If you change the direction, momentum will change. If you change the magnitude, momentum will change. I hope this is clear to everyone. Now, you can see here momentum is not equal for both the masses. Now let us look at the formula to calculate linear momentum. As we know, it's the product of mass times velocity. As velocity is vector, momentum is vector. The standard unit is kg per second. Here, momentum and velocity both will depend on a reference frame, which simply means from where we are observing the motion. So let's say you are standing on ground. That means the reference frame is at rest. Then to define the velocity of any object, you will be defining it according to your frame. But as soon as you jump on a moving frame, let's say you are on top of a car, then the velocity of the object will be different. So definitely velocity depends on frame of reference. Also, momentum will depend on it. Now here, we need to look at an important point. As force will be required to calculate momentum, this was said by Newton. So we will be looking at how the force will be affecting momentum. So first, a force can either increase momentum, decrease momentum, or it can change the direction. Means definitely direction changes means momentum will also change. So let us look at some cases. But before that, let us also look at Newton's second law. Newton in his second law given a relation between momentum and force. And that relation is net external force on a body equals to change in momentum over time. Here, the total average net force on a system is equal to the rate of change of linear momentum of that system. Here, change in momentum can be taken as P final minus P initial over the time. Now here, if the mass of the body remains constant, in that condition, we can open up the formula of momentum as mv minus mu, and taking mass common, we get v minus u by t, rate of change of velocity, that's acceleration. So the formula F net equals to ma. This formula is only valid when mass of the system is constant. But imagine a rocket that is moving up in space. There the mass of the rocket is not constant because as the rocket moves up, gases are coming out from the bottom. So definitely the mass of rocket keeps on reducing as the rocket moves up in the space. So if mass is not constant, in that condition, we will take change of mass upon time, keeping velocity constant. Then we get this formula for variable mass system. We will also look at an example from where you'll understand how we apply this formula. Now let us look at a problem based on the similar concept. Here this question is based on washing a car. Water leaves the hose at a rate of 1.5 kg per second with a speed of 20 meter per second aimed at the side of a car, which stops it. What is the force exerted by the water on the car? Here, initially, some mass of water is coming out from the nozzle, which is coming out with a speed of 20 meters per second. So here we can say that mass times velocity, that will give us the initial momentum of the water as soon as it comes out from the nozzle. Then, as the water will strike the side of this car, the final momentum for water will become zero. Why? Because the velocity of water will become zero as it comes in contact with the wall. So, as we know, according to Newton's second law, net force equal to change in momentum over time. Final momentum of water as it collides, that will be zero. Initial momentum we can calculate from the information given to us. 1.5 kg per second. From the unit you can understand this is mass by time that is given to us. How we get momentum? We multiply mass with velocity. So here, if you already know mass with the time, if you multiply it with the velocity, you can say this will become rate of change of momentum, mv by t, but we only need mv in the numerator. So what we do is we multiply mass with velocity. As time is already there, this time will go to the denominator. So this overall quantity gives us the net force. Here the net force that we get is negative 30 newtons. Why negative? This negative indicates that water initially it was moving in the right direction, but the force is acting opposite to that direction. That's why we are getting a negative sign. I hope this is clear to you. Now let us look at another problem. Gravel falls vertically on a conveyor belt at a rate of sigma kg per second. You can see these are the gravels that are falling on this conveyor belt. And the conveyor belt you can visualize moving like this. Determine the force that must be applied on the belt to keep it moving at constant speed v. What force must be applied on the belt so that the belt keeps on moving with this speed? Second, power that must be supplied by the motor in order to turn the belt. And third, the rate at which kinetic energy of the gravel changes. This is something we need to calculate. So let us start with the first part. What force must be supplied on the belt technically to move it with a constant speed v? Force, as we know, that's change in momentum over time. Change in momentum can be written like this. As mass on the conveyor belt keeps on changing, we are going to use the other formula, which is v delta m over delta t. What is delta m over delta t? That is rate of change of mass. That is given as sigma kg per second. As you can see here, kg per second means mass by time, right? So that way also you can relate. So you will be saying that v sigma is the net force. Unit will be Newton. This is the net force that must be supplied to the belt so that it moves with the constant speed v. Now, let us look at the second case. We need to find the power that must be supplied by the motor turning the belt. So how we get the power? The formula for power would be force times velocity. As we calculated force in the first part, sigma v, we multiply it with the velocity, we get sigma v square. Now, in the third part, we need to find the rate at which kinetic energy of gravel changes. Now, how we get this? As you can see over here, let's say we assume that in 1 second, the mass on the belt increases by sigma kg. Now, how we are framing this assumption? Based on the information given to us in the problem. Sigma kg per second. So every second sigma kg of mass falls over this belt. As we know the information for mass and time, we can say kinetic energy, we know half mv square is the formula. So here, assuming the mass as sigma that falls in 1 second, multiplying with the constant speed v, we can figure out the kinetic energy. So I hope this question is clear to everyone. Moving to the next part. Here we will be dealing with conservation of momentum, which is a very important concept. Let us visualize two masses, ma, mb, coming closer to each other with the velocity ua and ub. So before collision, they will have a momentum that is ma ua plus mb ub. As of now, we are taking both to be positive, but we know that ub will be negative. Here, when they both collide, after collision, let's assume them to be moving in the opposite direction with speed VA and VB. So can we find out the momentum in this case as well? Yes. By multiplying the mass with velocity, we can figure out the momentum after collision. Now here in this system, both masses, when they are coming close to each other, externally there is no force acting on the system. What do we mean by that? It simply means that when the masses are coming closer to each other, they are coming closer because here there is some mutual attraction between them, or something which is not due to the external force that is acting on the system. So here we can say as external force is zero. According to Newton's second law, net external force, that is change in momentum over time, we can say change in momentum will also become zero. Because if you equate this to zero, delta t multiplies with zero, you get delta p zero. That simply means finally after collision, the momentum is equal to initially momentum before collision. So I hope this point is clear to everyone. Here, before collision, the momentum was this. After collision, the momentum was this. So can we say total momentum doesn't change of an isolated system? Because in case of an isolated system, external force is zero. That means total momentum of the system remains same. Now let us look at this question. This question is a railroad car's collision based problem. A 10,000 kg railroad car A traveling at a speed of 24 meters per second strikes an identical car B at rest. If the cars lock together as a result of the collision, what is their common speed just afterwards? Now, here let's try to get a visual understanding of this problem. Car A having mass 10,000 kg moving with 24 meters per second. Car B having mass 10,000 kg which was initially at rest. This is the case before collision. When both cars are colliding, after collision they will have a common velocity as mentioned in the question, that they stick together, cars lock together, that means they are moving together this time with some velocity. So we don't know the value of velocity, we assume it to be V common. Before collision, after collision, we assume the momentum to be same. As here you can see this is a collision problem, and remember this, in collision cases we conserve the momentum. So initial momentum we can calculate by multiplying mass with the initial velocity. Final momentum we can calculate by multiplying mass with the final velocity. Here what is the initial velocity of B? That is 0. So this momentum is 0, and this momentum you can calculate, which is equal to the final mass into final velocity, like this. Here, in order to find the final velocity, we just equate it, and the answer that we are getting from here is 12 meters per second. So I hope this question is also clear to everyone. Now moving to the next problem, a moving body of mass m collides with a stationary body of double the mass and sticks to it. Calculate the fraction of the original kinetic energy that is lost. So it's a very good problem, but here we need to understand what needs to be done. They said calculate the fraction of original kinetic energy that is lost. That simply means we need to calculate loss in kinetic energy over original kinetic energy, that fraction. So can we say that initially the body which is moving to the right having mass m speed u, another body of mass 2m which is at rest. Here, when both the bodies will collide, let's say they stick together and move together, so they will have same velocity. Before collision, after collision, we equate the momentum because it's a collision problem. Here, when you equate the momentum, you get the value of V, that is u by 3, 1/3 of the initial velocity of first mass. After knowing velocity, we can calculate the kinetic energy before and after collision. Before collision, kinetic energy is half mu square because other mass will not have any kinetic energy. After collision, both masses move together with v velocity. So we assume both masses, sum will be 3m. Velocity will be u by 3. Taking that, we can figure out mu square by 6. That's the final kinetic energy. As you can see, kinetic energy is reducing after collision. What they were asking in the problem, loss in kinetic energy fraction. That means we need to take the loss value over the actual value, that gives us the fraction value. Here we can figure out loss in kinetic energy by taking difference of the final kinetic energy from initial one. So finally you have kinetic energy which is this, initial is this, so you get a difference that's 2 by 6 mu square. So I hope you are able to understand how we are getting this answer. Now fraction of the original kinetic energy that is lost, when we calculate this kinetic energy which is lost one over original one gives us 2 by 3. So I hope you got clarity about conservation of momentum. And in the next video, we will be discussing about collision. Do not forget to like this video if you understood the concepts properly. If you have any doubt, please let us know in the comment section below. Put your valuable comment over there. We will try to take your doubts in our upcoming sessions. Also, do not forget to download the PDF from the description below.